All right, welcome to the final recorded lecture here of our semester for new material, anyway, that we're going to be getting into. And this particular lecture, we're going to take a look at the second half of Chapter 10 and kind of really look down at almost the molecular level picture of what's happening with gases and kind of where some of their physical properties come from, what they're related to, in ways that we can hopefully better understand where things like that ideal gas law equation that we saw in the first half of Chapter 10 really came from. And so that's really going to be kind of our starting point here. So we're going to talk about something called kinetic molecular theory, which is really just a set of assumptions in terms of how we think about or how we treat gases when we're talking about their general behavior. And as long as we're under kind of normal conditions, pretty much all of these assumptions will hold true. And in fact, there's only a couple of them that aren't true under all conditions, and we'll talk about kind of what some of those situations are where really this kinetic molecular theory kind of maybe breaks down a little bit as we get to the end of this chapter and talk about this real behavior of gases and kind of exceptions to the ideal gas law, like when that gas law might not work. All right, so our list of assumptions. The first assumption that we make for kinetic molecular theory is that all of our gases are made up of these tiny little particles that can be either atoms or molecules, doesn't matter, and they're just moving about at random. So there's no kind of organized motion of any kind between the particles. Like each individual particle has its own motion that they're just kind of all randomly moving about, potentially colliding with one another. All right. The second assumption that we make, this one does have some potential circumstances where maybe it's not perfectly accurate, but under most conditions that we're in the lab for, this should hold true, and that's that the volume of the particles themselves is negligible compared to the total volume of the gas. And if we think about this, like the size of most atoms, like the radius of most atoms is somewhere down like around picometer range. So if we're measuring volumes that are like in milliliters or liters, that volume is so much bigger than the size of the atoms, like so many orders of magnitude different, that the size of the atom is irrelevant. It makes no difference whatsoever to our overall size or basically of our containers for the gases themselves. So we have to have some extraordinarily small volumes, or maybe some really just extreme pressures where we just have tons of molecules kind of all bunched together in a relatively small volume before this assumption starts to have any problems. So everyday just kind of calculations or situations, this assumption should pretty much always hold true. All right. The third assumption that we make is that gas particles are going to act independently of one another, meaning there's no attractive or repulsive forces between them. So this really comes about because the particles are typically just moving so fast that there's not time for them to really have kind of attractive or repulsive forces towards one another. The particles, because of their size being so small and the speeds they're traveling at being usually so high, that when they get near each other, they don't have a chance to interact. They basically, as soon as they're anywhere even close to each other, they've either just already passed each other completely or they hit each other and have a collision. And that's actually kind of gets us to our next assumption that when we do have those collisions between gas particles or between a gas particle and the wall of its container, then we consider those collisions to be what we call elastic. So something is elastic from a collision standpoint if all of the kinetic energy of that collision is conserved. Basically, the particles aren't losing speed from those collisions. That and really in terms of assumptions, like there shouldn't really be problems with this. It's possible that maybe you can lose some of that kinetic energy to things like heat or sound or things like that. But in this particular instance for gas particles, again, that amount's going to be so negligible for any calculations or situations that we'd be looking at. It's not going to matter. We're not going to notice that really have an impact on anything. All right, our last assumption for kinetic molecular theory has to do with temperature. And basically it says that the average kinetic energy of all of the gas particles in a system is proportional to the temperature of that particular system or sample, which really means that temperature itself is really just a measure in a way of how fast particles are moving on average. And we'll look at an equation that actually shows this relationship here in just a moment. But before we get to that, I want to kind of be able to take these assumptions and really just kind of a molecular level perspective to be able to think about a lot of the different properties and relationships we've already seen with the gas laws, right? So for instance, here we have a box that has a bunch of different gas particles already in it. And we want to look at, as we make different changes, what happens to other properties, right? So for instance, if I have a box here, and for pretty much all of these, at least for right now, we can think of things like pressure or volume as kind of like what might be changing. But if I have a box here, If I take this box and I just make the box smaller and try to keep as many other things constant as I can, like so temperature, for instance, I can keep constant. If I don't change what's contained in the box, so the moles are gonna stay constant. If I shrink the box, there's gonna have to be a change then in pressure, right? And that's Boyle's law that has like a volume and pressure relationship. Uh, as I make this box smaller, if we think at the molecular level, what's really happening? Pressure at the molecular level comes from all of these particles colliding with the walls of the box, right? And pressure can really be thought of as a force divided by an area. Well, we have a surface area for our box, and we have the force of all of the collisions, basically of all the particles hitting the walls of the box. If I make the box smaller, there's now going to be more collisions because with less space to travel in, the particles are going to collide with the walls of the box more often. If they're at the same temperature, they're still roughly moving it around the same speed or having the same kinetic energy. And in addition to that, if the box is smaller, the surface area is smaller. So if I have a smaller surface area and basically more collisions to create more force on those surfaces of the container, by making the forces bigger and the area smaller, both of those factors should lead to an increase in pressure. So decreasing our volume increases the pressure. This is what we saw out of Boyle's law, like that individual gas law, right? So we saw that as pressure goes up, volume goes down, or vice versa in this case. Or actually, sorry, that is what happened in this example. But those two are inversely related, right? Anytime one goes up, the other has to go down if we keep the other components kind of unchanged or constant. If we think about what happens with temperature changes, so let's say we're just under normal atmospheric conditions and we have a box that is able to potentially expand, like a balloon might be a good example of this. If the surfaces of this box are somewhat like a balloon, if we increase the temperature, we have a constant atmospheric pressure all on the outside of this box. But by increasing the temperature, the particles start moving faster. Well, so what happens if the particles start moving faster, but the external pressure stays the same? It's possible that if the box is able to expand, the box will actually just expand. Right? So this is the volume temperature relationship that we saw with Charles' law, like from our lab. As we increase the temperature, particles basically are going to be moving faster. So unless we want the pressure to increase, the volume has to increase instead. Like one of those two things has to increase. And that's, again, if you think back like the ideal gas law, pressure and volume are the two things that are on the opposite side of the equation from temperature. So as temperature goes up, either pressure or volume also has to go up. And so it just depends which one can change. If you have something like a balloon where it's a constant external outer pressure, it'll be the volume that increases, which kind of was what we see here between these two boxes. If we had a situation where the box was just actually a box that could not expand, then we'd have to see the pressure increase instead. Because if temperature goes up, the particles are moving faster, so that means more collisions, so more force. The force part of that kind of pressure equation of force over area. If the force goes up, the pressure will go up. All right, if we think about relationship to moles, right? So here for this box, if we add more gas to it, if the box is able to expand, it will expand, right? If the outer pressure stays constant. That's kind of a similar thing with what the temperature is, right? If we add more gas particles, think about the PV equals nRT equation, right? N goes up, either P or V has to go up. Well, if the box is able to expand, the volume will increase against that constant external pressure because there's just more particles in here. And again, to keep the pressure constant, like the volume would have to go up so that it would kind of lower the collisions and increase the surface area because the extra collisions that we would normally have in the same size box would normally cause the pressure to increase. So to keep the pressure the same, volume can increase instead. Or again, the other way to think about this, if this box can't get any bigger, if it stays the same size, now if we increase the number of moles, like the pressure would have to increase, right? There's just more things in the box. They're all still moving at about the same speed if the temperature hasn't changed. So more collisions means a bigger force, means a bigger pressure. All right, last kind of general comparison here, identity of the gases. And remember, this is one that we talked about at the end of the last lecture. The identity of the gases doesn't really matter, right? It's really just the total number of particles. So if the total number of particles between these two boxes are the same, even if half the particles in this box or more are a bigger, heavier molecule, it makes zero difference to the overall pressure or volume or things like that. It's just not going to have any impact. The identity of the molecules does not matter unless we have some kind of really extreme condition, right? And so we said there were some times maybe where this idea of kinetic molecular theory does sometimes break down. We'll get into those instances and see like when does the identity maybe matter, but for anything under normal kind of lab conditions that you're likely to ever encounter, like anything we would do for a general chemistry lab or probably any undergraduate lab of any kind for chemistry, we're always going to be able to use the ideal gas law for working with gases because we're just not going to have such extreme conditions where we have to ever worry about exceptions. All right, now I did mention when we were going through kind of the kinetic molecular theory assumptions that in the last one, kinetic energy and temperature are related, right? And so there's actually an equation that can model this relationship, which we'll see here. So kinetic energy is equal to 3RT over 2N. And the pieces of this equation, the N down here is Avogadro's number in terms of like what this actually represents. So this is a constant value. R is the ideal gas constant, which is also a constant value. Although if you use this equation, there's actually two values, remember, for the ideal gas constant if you look at your textbooks. Previously in our last lecture, the value of R was 0.08206 liter atmospheres over mole Kelvin for units. There's also another value of R that's 8.314 joules over mole Kelvin instead. So there's a slight unit difference there. Anytime you're doing an equation that deals with energy, like this one is, you want an R that's going to have joules in its units. So we'd actually use the 8.314 version of R anytime we ever use this equation. Realistically, probably not going to see this pop up too often. Probably it's more important just to understand the general relationship, right? R is a constant. This is Avogadro's number. It's a constant. So the only thing that kinetic energy actually depends on, the only real variable in this equation is temperature. And that's probably the most important thing. Kinetic energy of particles for a gas only depend on the temperature, and that's it. So regardless of what gases you have, if they're all at the same temperature, they should all have the same kinetic energy, is the general thing we can take away from that. Now, if we care about speed of the particles, now we can also look at some other things, right? So for instance, we have this equation up here that relates kinetic energy and temperature. So here's one equation for kinetic energy. But from earlier this semester, we also know that kinetic energy is 1/2 mv squared, like mass times velocity squared. In this case, in this equation, we use u because it's an average velocity instead of just the actual instantaneous velocity for particles. But if kinetic energy is equal to 1/2 the mass times the average speed of the particles, and it's also equal to this, we can actually now relate temperature, right, to the speed of our particles. And the one other piece that ends up in this equation, if we actually solve this equation for u, just doing a little bit of kind of basically I can multiply the 2 over, that's why the 2 goes away and there's no 2 over here. We can divide the mass part over, and then we have the velocity here where we're taking now the square root to get rid of the square. That's how we're getting to this equation. We have Avogadro's number and the mass of the particle both kind of involved in here, which is how we actually end up with molar mass. And so the average velocity of a particle, this capital M being molar mass, is going to be the square root of 3RT over M. Probably the biggest thing, again, for this equation, if you need these equations, these are ones that are probably going to be given. It's very rare that people usually have to memorize these equations, like even for an ACS exam, for like a final or something. Usually if this equation is needed, it's probably going to be provided. What they might not provide is if you don't need the actual equation, they might just be asking questions about how things are related. Right, so kinetic energy and temperature, they're directly related. If temperature doubles, kinetic energy would also double. Although remember, temperature here, if we're using it in this equation, would have to be the Kelvin temperature, not Celsius. Right, anytime we use plane temperature in an equation, has to be in Kelvin. Down here, our relationship is that the average speed of a particle is inversely related to the square root of the molar mass and related to the square root of the temperature. So if the temperature doubles, the particle speed doesn't double, it goes up by a factor of about the square root of 2 instead. But the other component there is the mass, right? The molar mass of that particular particle. So this is the first equation anywhere that we've really seen where the identity of the particle actually matters. And probably one of the biggest things to take away is that the heavier the particles are, the slower their average speed is if they're at the same kinetic energy, which is really meaning the same temperature. So for instance, if you have helium and argon, both kind of present in one sample. They're both just noble gases. They're gas phase normally. if you want to know what the kinetic energy of each is if they're both the same temperature, they'd have the same kinetic energy because the identity of the gas doesn't matter. But for the speed of the particles, there will be a difference because their molar masses are different. Argon is heavier than helium, so it's a bigger molar mass, so argon will move slower at the same temperature than helium would be how we could compare that. And again, we'll have a couple sample questions here we can take a look at to kind of relate these things. So putting all these things kind of together that we've been talking about, things we'd want to be able to answer. So here we have one, explain why decreasing the volume of a container while keeping its contents and the temperature constant will cause the pressure to increase. And again, this is from kind of a conceptual perspective. At the molecular level, if our volume shrinks, remember the pressure of our gas depends on the force of all the collisions of our particles at the walls of the container and really the surface area of the container itself. Well, if our container gets smaller, the surface area gets smaller, which causes the pressure to go up, as well as the force part, basically of all there's more collisions happening in a smaller box than there is in a bigger box, which means the force part of the pressure equation would also be bigger. So if pressure is force divided by area and the area gets smaller and the force gets bigger, both those things make the pressure get bigger. So that's why decreasing the volume while keeping other conditions constant should always increase the pressure of something. And so we have kind of almost this molecular perspective of a way to describe why we should see a pressure increase for really what amounts to like a Boyle's law kind of comparison. All right, and again, this is kind of a written explanation of what I just said. Other examples, again, these are kind of more comparisons, but that's really a lot of times what will come out of some of these things. If we want to know which particle have a higher kinetic energy at 25 degrees Celsius, helium or argon, well, what we were just talking about is that kinetic energy only depends on temperature. It doesn't depend on the identity of the gas. That was the big thing I was making in the last slide with those equations. Since kinetic energy has no relationship to the identity of the gas, if they're at the same temperature, they should have the same kinetic energy. That's all there is to it. They should be equal to each other. Neither one is going to have a higher kinetic energy. Now, if we want to know which of those two gases at 25 degrees has a higher average velocity, that's different, right? Velocity does have a molar mass component, and its general trend is that the higher the molar mass is, the slower the particle is going to move, right? Or if you're thinking about the other way, the smaller the mass, the faster it will move. And so here, the way I kind of describe it in the slide, they both have the same energy, but since kinetic energy can be thought of as 1/2 the mass times velocity, and if you want to put a U instead of a V for average velocity here, that's fine. I just showed this in general. Since helium's mass is smaller, its velocity must be bigger in order for the two to have the same kinetic energy. So smaller masses, faster speeds, or bigger masses, slower speeds is kind of the general trend for the speeds or the velocities of our particles. All right. A couple last things that we also going to relate to this idea of diffusion and effusion. So these two things are somewhat they are very similar. I'll start by talking about diffusion in terms of kind of what it is, and then we'll talk about effusion, which is something that we'll have an equation related to it also on the next slide that we'll talk about. For diffusion, what's happening is basically you have, you imagine this being closed off between kind of these two halves of this box. If we have two separate containers, one that has a gas and another has a different gas, as soon as you open basically this a little gap between the two different containers, what's always going to happen, since all of our gas molecules are moving around just at random, these gas molecules that are in the left box, over time, they're going to diffuse their way over here and kind of be evenly mixed throughout all of this entire container if it's all connected. And it may take a little bit of time for it to reach that point, but it won't take too terribly long. Things will tend to diffuse fairly quickly. And so we will see kind of an equilibration of, like here we see particles of the red particles moving from the left to the right, the blue ones moving from the right to the left, to basically start kind of intermixing the two different gases. And after just a short period of time, these blue particles should be pretty much evenly distributed between the two sides. And the same thing for the red particles. And it's almost like kind of an equilibrium thing, which is something we'll talk more about in 1212. But it really just comes down to, like, over here, we have a bunch of particles, right? So there's more particles that are going to be making it through this little slot to the left than there are that are going to be coming back to the right, because there's just not many blue particles on this side. And eventually what will happen is if we get enough blue particles over here, they'll be coming back to the right at the same speed they're going to the left. And we'll notice that the general distribution of all these blue gas particles will be the same on both sides. Same thing will happen with the red. So after a short period of time, all of this will be pretty evenly mixed of red and blue gas particles. They won't stay separated for very long. That's the process of what we call diffusion. So just normal molecular motion causes all of these things to kind of just evenly mix between or basically completely throughout any container. Now, effusion is slightly different. Effusion has to deal with if we have a sealed container and we basically poke a small hole in that container and we have a vacuum on the other side of the hole to help pull some of the gas molecules through that little hole. And so effusion refers, and we'll often talk about rates of effusion and how fast gas particles are able to basically escape through that little tiny hole. And it turns out effusion, we are going to have an equation that we're going to talk about in terms of kind of what affects rates of effusion. And really probably what I relate it to is just the faster that particles move, the faster they're going to effuse, right? And so we saw before on the previous couple slides, the speed of particles depends on temperature. Like the higher the temperature, the faster they will move. But it also depends on molar mass. So particle identity does matter to effusion. The heavier the particle, the slower it moves, so the slower the rate of effusion is going to be. So that's just kind of the general trend. And we can actually see a specific relationship through what we call Graham's law. And so Graham's law states that the rate of effusion for any particle is inversely proportional to the square root of its molar mass. And again, I think of this, remember the square root of the molar mass, the reason it's the square root here is the speed of the particle was inversely related to the square root of the molar mass of the particle. And so that's really where this general relationship comes from. And in particular, probably the biggest application of this is to compare rates of effusion of different compounds and use that information to find the molar mass of something. And so that's what we'll actually take a look at doing a sample calculation of in just a second. But we can do that with this relationship right here. And so this basically says that the rate of effusion of one gas divided by the rate of effusion of another should be equal to the square root of the molar mass of the second gas divided by the square root of the molar mass of the first, which looks a little strange, but it's really just taking this top part and kind of using it for both of these. We're just imagining doing basically gas 1 divided by gas 2 on both sides, right? So here we have the rate for gas 1 divided by the rate of gas 2, but on the right side it would have been 1 over the square root of mass 1 divided by 1 over the square root of mass 2, which is why the square root of mass 2 ends up at the top. So some sample questions, like what should we want to be able to do with this information? So here we're just asked, which gas do we expect to diffuse faster under identical conditions, helium or argon? And then it also asks, how much faster would it diffuse? Well, first, if we look at helium and argon, just in general, we already said that the rate of effusion depends mostly on the molar mass, and really a lot on kind of how fast the particles are moving. But if they're at the same temperature, only the molar mass is going to make a difference. So between helium and argon, we said that the molar mass of argon is bigger, and the bigger our molar mass is, the slower the particles move, and as a result, the slower the effusion is. So helium should have the faster effusion because it's the smaller particle. But now we want to figure out how much faster. And this is where we can use Graham's law, that equation on the previous slide. And I apologize that this equation actually looks, this square root bar extend a little bit further than I intended. But it's basically here, this square root of the molar mass of argon over the molar mass of helium should be equal to the rate of helium over the rate for argon. And so this is actually basically just this part. And again, apologize for the square root being over a much larger chunk than I intended there. I didn't catch that when I put it together. But what we're going to see here is if we take the square root of the molar mass of argon divided by the square root of the molar mass of the helium, and you can put this all under one square root or just take the square root of each individually. It actually makes no difference. It'll come out the same either way. What we're going to end up getting here is that the rate of helium over the rate of argon, this ratio is about 3.16, which means helium should effuse at a rate that's 3.16 times faster than argon does. And notice it effuses a little more than 3 times as fast, and it's about a 10-fold increase in molar mass going from helium to argon. And so that's kind of a bit of how we can see that relationship happen. We can kind of keep that in mind for the next question also to help give us kind of some perspective on what to expect for an answer. So we'll look at a second example of using this, and we want to know a gas of an unknown molar mass is allowed to effuse over time from a small opening, and it takes 105 seconds for 1 liter of the gas to effuse. If under the exact same conditions it takes oxygen gas 31 seconds for 1 liter to effuse, determine the molar mass of the unknown gas. So I'm going to show this one on kind of my whiteboard, so maybe it'll make a little bit more straightforward sense. for what we're actually doing. So we're going to use Graham's law. I'm going to get my iPad set up here quickly. And so if we take a look at trying to set this problem up, we have gas 1. So we have gas 1, which is going to be our unknown. And we're told that this takes 105 seconds for 1 liter to diffuse. And then we have gas 2, which in this case is oxygen gas. But one thing you will want to be careful of in this case, oxygen gas is O2, right? It is a diatomic. And so we have O2 that we're told takes 31 seconds for 1 liter to effuse. And we want to be able to use that Graham's law relationship, right? Graham's law was saying that basically rate for gas 1 over rate for gas 2 is going to be equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. And it really doesn't matter which one we pick as gas 1 or 2. It doesn't make any difference. In this case, actually, I think I'm going to, based on how I've shown the equation, I'm actually going to switch how I've labeled my gases over here, just because it's easier to probably solve for this part, M2, equation-wise. So I want to be able to solve for M2 using all the information that I have here. Now, there's one thing I do have to be careful of. This equation for Graham's law deals with rates, not times, right? So if it takes 105 seconds for 1 liter to diffuse, right, that rate is basically going to be some amount divided by a time. So really, the rate for let's say our rate for gas 1, the oxygen, is actually going to be 1 liter divided by 31 seconds, is how we would calculate that, right? Because the amount of time it takes, the longer time it takes, the slower the rate, because those two are inversely related. So how I could set this equation up is my rate for gas 1 could be 1 liter divided by 31 seconds. Right, so that would be my rate of gas 1 divided by, for the second gas, 1 liter over 105 seconds is going to be equal to the square root of the molar mass of gas 2 that I don't know. Right, that's what I'm trying to find in the equation, divided by the molar mass of gas 1, which is the O2. And again, this is where we do have to know oxygen is diatomic, right? So O2, its molar mass would be 32 grams per mole. And now I just want to go through and actually solve for M2, right? So I just want to solve for this. So if I want to solve, I can take this part over here and calculate this part, which I think comes out to, I have in the slides over there, you might even be able to see it from here, about 3.39 roughly. Should be equal to the square root of M2 over 32. And now I can square both sides. So 3.39 squared should equal just M2 over 32.0. And then I can multiply the 32 over. So, oops, apologize. Sliding things around a bit too much. So M2 should be 3.39 squared times 32.5. Oops, 32.0, sorry, grams per mole. Which at the end of all of this should come out to about 367.7 or 368 roughly grams per mole for a molar mass, which seems like a big amount, and for a gas that kind of is. But if we think about kind of our answer to the first example, we said argon's about 10 times heavier than helium, and helium as a result moved a little more than 3 times faster. Well, if we look at the rate increase over here, right, this is effectively the rate increase for oxygen versus our unknown gas. So if oxygen moves a little more than 3 times faster than our unknown gas, we should expect our unknown gas to have a mass that's roughly about 10 times as big. Well, oxygen's mass was 32, so 368, it's about 10 times as big, a little more than that actually. And so that answer does kind of fall in line and kind of make sense for some of those patterns. And so in this case, 368 grams per mole would be our unknown mass. And again, we got that using kind of this Graham's law relationship up here. Again, the tricky part, and this is probably as hard of a Graham's law problem as you would ever see on anything for like a quiz or a test or like an ACS exam, mainly because it not only does it make you know and use this Graham's law equation, it also makes you know that like the times it's giving you are not the rates themselves. The rate is actually kind of an inverse of the time. That's why we did like the volume divided by the time instead of just plugging in a rate, because we didn't have the rate value itself. All right, so that's the end of that example. I have just a couple last slides that we're going to go through still. So I'm going to jump back to our PowerPoint. We saw our answers here, and we saw there's the answer that I just showed on kind of the whiteboard portion. And the last couple things I want to talk about in this chapter have to deal with the exceptions to our kinetic molecular theory and kind of like when do we have things that maybe the ideal gas law doesn't properly work for. And so I want to talk about what we call normal gases. So under normal temperature and pressures, pretty much every gas behaves kind of according to our kinetic molecular theory, and if kinetic molecular theory is kind of obeyed, that means that gas should follow the ideal gas law. The ideal gas law equation should work for that gas. But there are a couple times when that breaks down. So the places where our kinetic molecular theory and really the ideal gas law equation itself kind of fall apart and don't work properly is if we get extremely high pressures that are kind of almost coupled with small volumes to an extent as well, where basically our gas molecules are so condensed that now the size of the particles themselves does actually matter. And since we ignored the size of the particles previously, this does create a problem for the ideal gas law. So this is one extreme condition, but again, the pressures we have to get to are enormous for something like this to happen. And then the other condition that can cause a problem is extremely low temperatures. If we have really, really low temperatures, like close to like absolute zero low temperatures, it's possible that gas particles start moving slow enough that now the attractive and repulsive forces that could happen between gas molecules can't be ignored anymore. And again, that only happens at extremely low temperatures where the gas particles are now moving around so slowly that their attractive and repulsive forces do matter. They're not just going to zip by each other or bounce off of each other before those forces matter. And again, this is not something we're going to see in normal lab conditions. And it's also going to be hard to actually have gas molecules near absolute zero anyway, if we think about it, right? Because if we get that cold, how many things are still a gas? Most things are going to become either like a liquid or a solid, more for most of them. And so these extreme conditions, like we don't encounter things that are this extreme for these to matter very often. You have to be doing some kind of like very specific, particular kind of experiments with very particular setups for either one of these conditions to really become a problem, which is why the ideal gas law really works so well, is because it works for almost every situation, with the exception of these kind of really extreme ones. Now, if you are under these extreme conditions, there are ways to like try and update the ideal gas law. You sometimes hear people talk about something called the van der Waals equation, or a corrected version of the ideal gas law that looks something like this. So instead of having like PV on this side equals nRT, you have one side that's just pressure, and you can actually see some other components here for ideal gas law. And so these extra components, like for instance, like the A and the B in particular, are correction factors. And so the B term here is meant to just account for the volume of gas particles. And so that's basically like the size of portion of like your actual gas particles. And then you have the A component over here is like the other different variable, like the N and the V are still just moles and volume through all of this. But the A portion of this is to help account for any intermolecular attractions or repulsions. So anything that has to do with what, when we get to 1212, we call intermolecular forces. Any intermolecular forces that may exist get accounted for by this term basically in the equation. Now, you will probably never really have to use this equation for anything that comes up, because we really aren't going to be doing any experiments for general chemistry or really just like in general, unless you're working like with some of those really extreme conditions we just mentioned, to where we really need these correction factors. But if you are working under those kind of extreme conditions, there are models already kind of in place to try and help account for that. And basically, whatever your gas is, there's A and B values already known for those gases if it's a common gas anyway, uh, that you can use to basically calculate these values and use this modified version of the ideal gas equation. But again, practicality, probably not going to really need this equation or this version of the ideal gas law equation hardly ever, because we're just not likely to have the extreme conditions necessary for us to be taking these added precautions to our calculations. But even in the instance there are those extreme conditions, we do have ways to at least do that. All right, so that pretty much wraps up all of our general content for Chapter 10. This is a little bit shorter chapter, I think, than some of our previous ones. So our last exam that'll be coming up later this week. For my sections, it'll be pretty much all of chapters 8, 9, 10. I believe probably the other sections will be very similar to that as well. My hope is that on Friday of this week, I will have kind of a quick summation of kind of topics as far as things for the final exam. I'll have kind of a recording where I'm going to try to put out kind of a list of topics to everyone for my section and others too, and see if there's topics people want just kind of talked about more, or maybe just example problems. And then I can try to put something together to maybe just show a few example problems of some of the different topics that people are most interested in seeing, just to give some extra help to hopefully help people prep for our final exams that are going to sneak up very quickly, unfortunately, to be honest. And then hopefully we should have some information out to everyone in the next couple of days as well about the final exam itself, if you haven't heard from your professors already, because we have finally started getting some of that stuff put together as a department, and we should have some good information for everyone here if you haven't seen it already by the time you see this video. But that's all I have for Chapter 10. I hope everyone is hanging in there as we get close to the end of the semester, and then we'll see you all at hopefully that review at the end of the week.